This video is about operational definitions of attributes or constructs that cannot be observed directly. As you have seen in your analysis of a modern newspaper, very few attributes that need to be quantified can be measured directly. And many cannot even be observed directly. Or, if they are observed, many are changed in fundamental ways by the process of being observed. For example, in virtually every field where researchers have investigated differences between high-ability people and average-ability people, the high-ability people not only do things differently, but they also see, or interpret, things differently. This includes chess players, artists, musicians or teachers. And it also includes students who are learning mathematics or other school subjects. The development of these kinds of interpretation systems is an example of something that a person outside the physical sciences might want to measure. In general, operational definitions have three parts. First, they specify a situation in which the attribute, or its effects on other attributes, can be observed reliably. Second, they specify procedures for sorting out information that is relevant from information that is not relevant, like sorting out signal from noise in communications. Third, they specify a mapping to some type of quantitative scale or classification system. For example, to measure a person's interpretation abilities, the first thing that is needed is a situation in which the person's interpretation abilities will be expressed in forms that can be observed. These interpretations might come in the form of written or spoken descriptions, or drawings, or models, or analogies. But, if these descriptions, drawings, models, or analogies are to be assessed, then they need to be produced for some purpose that is clearly recognized by the person being assessed, or else there will be no basis for judging the strengths and weaknesses of alternative descriptions. And, a purposeful model, or description, is essentially a tool. So, if the situation being modeled is an important one, then the tool is powerful. And, if the tool is designed to be shareable and reusable, then it also is transferable, or generalizable. So, the act of developing this tool results in changes in the attribute being assessed. To measure it is to change it. This sounds like a social version of Heisenberg's famous uncertainty principle in quantum physics. And, in many ways, it is. Heisenberg's uncertainty principle applies especially to subatomic particles, or to attributes associated with them. It states that, for certain pairs of physical properties, such as position and momentum, or time and energy, the more precisely one property is measured, the less precisely the other can be measured. Heisenberg's observations might seem to be simple, straightforward, and inconsequential. But, in quantum physics, they led to shockingly new ways of thinking about cause and effect, b, past, present, and future, and c, inescapable interactions between observers and what's observed in physical experiments. From neutrinos in quantum physics, to dark matter in astrophysics, the world is filled with things and attributes which cannot be observed directly, and which can only be known through their interactions with other elements. In fact, many have meaning only in the systems in which they reside. So, they cannot be studied by extracting them from these systems. Consider the neutrino. Neutrinos are similar to electrons, with one crucial difference. They do not carry electric charges. Consequently, they are not affected by electromagnetic forces, and they are only affected by a weak, subatomic force of much shorter range than electromagnetism. So, they almost never interact with any other particles. In fact, most neutrinos pass right through the Earth without ever interacting with a single atom of it. Yet, neutrinos play important roles in quantum physics, and they are defined in terms of interactions that they have within systems of other elements. How can physical scientists measure or observe objects which have almost no mass and which rarely interact with other objects? The answer is to do with the three-part definition of what it means to operationally define a construct. Operational definitions must 1. Specify a tool which allows the presence of the construct can be detected. 2. Specify a tool for sorting out relevant from irrelevant information. 3. Specify a tool for classifying or quantifying the preceding information. In the case of a neutrino, step 1 has been achieved by burying a giant swimming pool-sized sphere 2,000 feet below the surface of the Earth, and filling it with a special type of heavy water in which interactions with neutrinos can be seen. Step 2 has been achieved using something like a bubble chamber in which results from interactions can be seen. Step 3 has been achieved by assigning the preceding information to useful and informative quantitative scales. For the quantification processes that we'll be emphasizing in this course, 3 different types of quantitative scales will be especially important. Nominal scales often are used in ways that are like names on the jerseys of soccer players. But sometimes, they also may give additional information such as in addresses of houses, 1245 North 3rd Street Apartment 401. Ordinal scales, for example, first, second, third, and so on, specify an order for the items. But, distances between items are not specified. So, you cannot add or multiply measures. For example, 2 plus 3 is not necessarily the same as 5, and 2 times 3 is not necessarily the same as 6. Rational scales. The 0 point on the scale is significant, and it usually refers to none of the relevant attribute. Furthermore, quantities can be added and multiplied. Operational definitions are different than dictionary-style definitions. Operational definitions don't simply describe the relevant attribute. They also specify how the attribute can be measured or classified in relation to other attributes or quantities. Example 1. What would you do to compare the distortedness of several photographs? Notice that it is one thing to know what distortedness means, and quite another to know A. How to compare the distortedness for several photographs, or B. How to measure the distortedness of an arbitrarily given photograph. Example 2. In a gymnasium, how would your operational definition of boredom be different than your operational definition of lack of focus or lack of interest? Example 3. In a counseling situation, how would your operational definitions be different for forcefulness versus aggressiveness? Example 4. A dictionary-style definition of what it means to be a fresh egg does not necessarily tell you how to test the freshness of an egg or how to measure its freshness. To see this, conduct a brief internet search to find out how to test the freshness of eggs. Then, for the method that is given, look for the 3 parts that make up an operational defined construct. When you do this, notice that, sometimes, one or more of these parts are not stated explicitly. The following resources are useful to develop a better understanding of why and how physical scientists deal with constructs and attributes that cannot be observed directly and that are changed in fundamental ways when they are observed indirectly. The first chapter in the book, Mr. Thompkins and Wonderland by George Gamow. This book provides elementary but deep descriptions of several of Einstein's most famous thought experiments about ways that modern scientists have reconceived traditional notions about simultaneity, and accompanying ways of thinking about objective observers. Similar thought experiments are acted out in a number of short internet-based videos such as the ones that can be found at the websites shown here. Both of these videos help to explain why electrons and other subatomic elements came to be thought of as having both wave-like and particle-like properties, and how they can be thought of as existing at multiple locations at a single point in time, and why observers necessarily induce changes in elements they try to observe. Taken together, these examples from physics show that learning scientists are not alone in their need to quantify attributes which cannot be observed directly and which are changed through processes of indirect observation. In fact, such examples abound in ecological sciences, economic sciences, and other fields dealing with complex adaptive systems, where scientists often are actively engaged in designing and developing the systems they seek to understand, where systems act back when they are acted upon, and where feedback loops often lead to results which are impossible to predict. But, this does not mean that quantification is impossible. It means that care must be taken to use procedures based on realistic and appropriate assumptions.